Okay, we're going to start with lesson 19 now. So we've talked about esters and how they react. Now it's time to move on to carboxylic acids and some other types of functional groups here. Carboxylic acids, if you just add a carboxylic acid to a base, it gives you this carboxylate, right? Well, that doesn't react well with a nucleophile because basically you just populated more of a negative charge on that carbon. So it's not exactly going to be a great electrophile anymore. So hydrogen needs to be present in order for carboxylic acids to work. A Fischer Esterification is basically just the opposite as what we just did to make COH. Notice this entire thing, again, is in equilibrium. So what you do to make this happen, which is just the opposite of what we had before, is you add in a whole bunch of extra methanol or alcohol, whatever that alcohol is. If it happens to be a lower boiler than water, then you can again, since you actually are producing water here, see how the H2O is coming out? You could boil off the water. Again, you're going to use Le Chatelier's principle, as that's going to drive that reaction to have excess alcohol. So really, just you're using Le Chatelier's principle here in either respect. And same thing happens. So we have this oxygen come and grab a hydrogen, and then once you have this guy even more polarized, that makes a really good electrophile right there in that carbon. The alcohol would come and attack that carbon, electrons would go up. A base, whatever that may be, it's probably going to be something, either a Cl minus or it's going to be some of your solvent. You can come and grab that hydrogen, electrons go back. So now we have sort of a carbon with 3 oxygens attached, not exactly the most stable type of formation. These electrons go and grab that hydrogen, electrons go back. You end up with basically a water molecule right there that's sort of stuck on, even though it's got a positive charge on the oxygen that wants to leave. So in order to kick it out, these electrons come down, it kicks that out. You end up with a hydrogen there on that oxygen. A base comes and removes that hydrogen, and you end up with your ester type of product. I just want to make sure that you all can see this because I know that the screen is kind of perfectly in balance here. Okay, so carboxylic acids and amines don't really need to know this type of reaction as far as its mechanism is concerned, because here's what happens. We have a carboxylic acid and we have an amine. The two come together and make a salt because the hydrogen here donates itself to the nitrogen, so it makes this crazy salt thing. Once you heat that up really, really high, what essentially is happening is we have 2 hydrogens here and the oxygen here will eventually be driven off as water. And that makes a new bond here, and that's the amide bond that you see right there. Okay? So that's what's happening there. Now, on to amides. Amides are actually pretty stable. That's the reason why everybody wants to be like them. We can make amides so easily, which is pretty awesome because that's basically what's making up your peptide bonds that's linking together your amino acids in your body. So we actually don't want those to degrade very easily. They can in acid, however, which is another good thing because you happen to have this little acidic area in your body called your stomach that tends to break down other proteins that may be entering your body from plants and animals so that you can digest them and reuse those amino acids or whatever it may be. Okay, so this is an acid catalyzed amide hydrolysis, or you could also do it with an alcohol, so an alcoholysis. So we have an amide, and we can use either an alcohol or just water, and then you end up with an ester, or you could end up with carboxylic acid as well there if you just use water. And here's what the mechanism looks like. Again, you've got an acid, so the oxygen's coming and grabbing that hydrogen, makes this guy much more positive, so that any type of nucleophile can come in here, any being water, alcohol in this particular reaction, right? When you do that, electrons kick up, then you end up with a water molecule with a positive charge on it. Chlorine or any base can come and remove that hydrogen. And so now you have a situation that looks like it could be stable. But in reality, when you have large amounts of acid around, it's not. Because remember, amines are relatively basic, and especially with like a harsh acid like HCl around, they're going to come over and grab that hydrogen, then the electrons go back to the chlorine. Well, now we have a good NH3 here, and NH3 is pretty happy on its own. So the electrons can come down, kicking out the NH3. Something that's important to note is that NH3, if you're in any type of beaker or that type of thing, NH3 can actually evaporate on its own. So that's somewhat driving this reaction, excuse me. But these electrons can then also come back and grab that hydrogen. Electrons go back, and you end up either with a carboxylic acid, or had you used, instead of water here, if you had used alcohol, then it could have ended up making an ester right there. Okay. Finally, I also want to talk about a little bit about acid anhydrides. These guys are very similar to what you've already seen with an acid chloride. So really it reacts just sort of like the basic standard reaction that we looked over at the beginning, as far as, you know, a nucleophile comes in and then a leaving group leaves, and it can be replaced pretty easily. You've never seen these before, so first you need to know how to name them. If it's symmetrical, basically what an anhydride is you've taken one carboxylic acid and another carboxylic acid, right here, and you've removed water from the two, hence the term anhydride, right? And actually, it's thought that acetic acid, vinegar, exists a lot of times in the anhydride state. So once we have this anhydride, in this case, it's symmetrical, right? And that's come together from two different propanoic acid molecules coming together, releasing water, and leaving behind this propanoic anhydride. We call it propanoic anhydride because it's put together by 1, 2, 3, that would be 3 carbons on this side. So if I were to name that, it would just be propanoic acid, right? So propanoic anhydride means that 2 of those have come together, lost to water, and that's what they look like. But if they're not symmetrical, then you have to name basically the 2 different groups that you're getting this from. So in this case, we have ethanoic acid, and from here it would be butanoic acid, that have come together and lost to water, right? So we just put that in alphabetical order. It would be butanoic, ethanoic, anhydride. And when usually we like to use symmetrical types of reactions, or so symmetrical types of anhydrides for reactions, simply because it's a lot easier to keep track of what your product is. Otherwise, you could have this guy be a leaving group, or this guy be a leaving group, and that would basically end up with a whole bunch of mess when you're looking at what your products might be. Okay, so when we're looking at different types of reactions, besides the ones that are very common, this is sort of just running through one of the ones that's more common. If you were to do this with an alcohol, we could take these electrons and up they go, right? Well, it's going to leave a negative charge there, okay? We also have a positive charge down here, so we've got to have some base come in, pull off that hydrogen. As these electrons go down, that entire group becomes your leaving group. See what I mean? That's your entire group that's leaving. Excuse me. And in this case, you would end up with, there's your ester. Since you have extra acid around, you end up also with a carboxylic acid. So you end up with 2 products, and depending on what you actually want to isolate, that might be something that you use your extraction technique to isolate one over the other, right? Because this one will go to a basic water solution, and this one would tend to stay in an organic layer, depending on what you have, of course. Okay, useful side reaction that we use a lot of times in this type of in these types of methods for our synthesis is simply that, remember, Cn minus will replace any type of halide or good leaving group via SN2 types of reaction. So we've got Cn here now. Here's the cool reaction. H2O, HCl, and heat gives you carboxylic acid. Because it does. And with this carbon right here from the Cn transforms itself to this carbon right here. Okay? So it's actually a different carbon than, well, it's the same carbon, I'm sorry. It's not a different carbon that you're getting from here. I just want to point that out because a lot of times it's really hard to see here. Okay, on to lesson 24.